Picture shows a magnetically levitated train moving on a magnetic track. Observe that the train is levitated from the track. Introduction. In this lesson, you will understand sources of magnetic field due to current in a straight wire B equals mu naught I over 2 pi A. A circular loop B equals mu naught Ni over 2R, and a long solenoid B equals mu naught Ni. Understand the force on a current-carrying conductor placed in a magnetic field, and F equals ILB sine theta. Derive and use the formula F over L equals mu naught I1 I2 over 2 pi d for the force between two parallel current-carrying conductors. Click the switch to close or open the circuit. Observe what happens to the compass. Now drag the compass around the conductor. What do you observe? Answer. When the switch is off, the compass remains pointing north. When the switch is on, the compass points in anti-clockwise direction, forming a circle around the conductor. Click the power supply to change the direction of the current. What happens to the compass now, as it is dragged around the conductor? Answer. The compass now points in a clockwise direction, forming a circle around the conductor. Click anywhere along the current carrying brown conductor to view the magnetic field pattern around the conductor. What do you see? Answer. The magnetic field consists of concentric circles perpendicular to the conductor. Maxwell formulated a rule for the direction of these field lines. It is commonly referred to as the corkscrew rule. The magnetic lines are in the direction one would turn a corkscrew to move the screw in the direction of the current. Another way is to point the thumb of your right hand in the direction of the current along the wire. The curl of your fingers then indicates the direction of the magnetic field, the right hand grip rule. How does the magnetic field change when the magnitude of the current in the conductor changes? Move the rheostat slider and observe what happens. Answer. When the current is increased, the magnetic field around the conductor becomes stronger, and when the current is decreased, the magnetic field becomes weaker. How does the magnitude of the magnetic field change with distance from the current-carrying conductor? Click the switch and drag the compass towards the conductor and observe what happens. Answer. The deflection of the compass needle becomes bigger as it is moved nearer to the conductor, showing that the magnetic field due to the current becomes stronger. What can you say about the magnetic field as you get nearer to the current-carrying conductor? Answer. The magnetic field becomes stronger as we move nearer to the current-carrying conductor. What is the magnetic flux density B of the magnetic field and what is its direction? Click at any point in the magnetic field for your answer. The magnetic field is at right angle to the perpendicular line joining the point to the conductor. The magnetic flux density B equals mu naught I over 2 pi A, where I is the current. Mu naught is a constant called the permeability of free space and is given exactly by mu naught equals 4 pi times 10 to the power minus 7 Henry per meter, and A is the perpendicular distance from the point to the conductor that carries the current. Click the switch to see the direction of current flow and the pattern of the magnetic field formed. Click at the center of the loop on the left. At the center of the loop, the magnetic flux density B of the magnetic field is given by mu naught I over 2R, where I is the current, mu naught is the permeability of free space, and R is the radius of the loop. If the loop consists of n turns, then B equals mu naught Ni over 2R. Note that this is the magnetic flux density at the center of the loop, and away from the center the magnetic field changes in both magnitude and direction. A solenoid consists of a large number of loops tightly packed together over a distance L, such as that shown. Click the Show Field Pattern button. You can see that the magnetic field formed by the solenoid is quite similar to the magnetic field of a bar magnet. Thus, a solenoid acts like a bar magnet with the south pole at one end and the north pole at the other end. The end of the solenoid where current flows clockwise behaves like the south pole of a magnet. If the current flows anti-clockwise, then that end is the north pole. Click the Show Animation button and observe. With sliders set at 10 turns per centimeter and 1.0 amperes, click the switch and observe what happens. Explain why. Answer: at the end of the solenoid facing the magnet, the current flows in clockwise direction. A south pole is produced at that end. Like poles repel. Increase the number of turns per centimeter and observe what happens to the magnet. Answer: the magnet is repelled further. Increase the current and observe what happens. Answer: the magnet is repelled further. From the observation, what conclusion can you make? Answer: the magnetic field produced by current in the solenoid is stronger when 1. The current in the solenoid is increased. 2. The number of turns per unit length of the solenoid is increased. Click the Graph button to observe the variation of the magnetic field B along the axis of the solenoid. The magnetic field is fairly constant inside the solenoid, except near the ends. Summary. The current carrying conductor produces a magnetic field. The direction of the magnetic field can be determined by using the right-hand grip rule or the corkscrew rule. For a straight conductor, B equals mu naught I over 2 pi A. For a circular loop, the magnetic field at the center, B, equals N mu naught I over 2R. For a solenoid, B equals mu naught Ni inside the solenoid. B equals half mu naught Ni at the ends of the solenoid. Click the On button and observe what happens to the brown section of the conductor. The brown conductor moves inwards. Click the check boxes to show the direction of the magnetic field and Lorentz or magnetic force. Click the Change Current Direction button and observe what happens. The direction of the current is now reversed. The brown conductor moves outwards. Fleming's left-hand rule can be used to determine the direction of the Lorentz force on the conductor. The expression for the force acting on a wire can be derived by first considering the force on one single free electron drifting along the wire. Then consider the total force on all the free electrons drifting across the wire. The derivation is shown above. If the direction of I is at an angle theta to B, the force is still in the same direction, but its magnitude is now given by F equals I LB sine theta. Click the checkbox to show component of B perpendicular to I. Choose different values for I and theta, then choose your answer for F from its pull-down menu. Summary. A current carrying conductor placed in a magnetic field experiences a force. The direction of the force, F, is always perpendicular to both the current, I, and the magnetic field, B. Fleming's left-hand rule can be used to determine the direction of the force, F. If conductor is perpendicular to B, then F equals ILB. If conductor is at an angle theta to B, then F equals ILB sine theta. What will happen when current flows in two parallel conductors near to each other? Click both switches S1 and S2 and observe what happens. When the current in the two copper strips is in the same direction, the two copper strips attract each other and move closer. What will happen if the current in the two conductors flow in opposite directions? Click the power supply to see what happens. When the current in the two parallel conductors is in opposite direction, the two conductors repel each other and move further apart. We shall now derive the formula for the magnitude of the force acting on two current-carrying conductors parallel to each other. First, we consider a straight wire carrying a current I1. This wire has a magnetic field around it. What is the magnetic flux density B1 at the point P? Click the answer button. Another wire of similar length L is now placed at P parallel to the first wire. A current I2 now flows in the second wire in the same direction as I1 in the first wire. The magnetic field at every point along the second wire has the same direction and magnitude as B1. Earlier, you've learned that a conductor of length L carrying a current perpendicular to B experiences a force acting on it given by F equals BIL. Therefore, what is the force acting on the second wire? Click the answer button. By similar arguments, the first conductor that carries a current I1 and placed in the magnetic field of the second conductor B2 will experience a force F1 equals mu naught I1 I2 L over 2 pi d in the opposite direction as F2. What is the force per unit length acting on the two parallel conductors? Answer: F over L equals mu naught I1 I2 over 2 pi d. Click the solution button. Summary: when currents flow in the same direction in two parallel conductors, the two conductors experience a force of attraction that pulls them closer. When current flows in the opposite directions in two parallel conductors, the two conductors experience a force of repulsion that causes them to move further apart. The force acting on two long parallel conductors depends on the currents in the conductors and the distance between them. The force per unit length on each parallel conductor is given by F over L equals mu naught I1 I2 over 2 pi d.